Hello guys, welcome to second law of thermodynamics, entropy. Now for our SLC syllabus, we only need the basics of entropy, surface level things, because entropy can be a broad and very mind-boggling term in physics, part of physics. So here basically entropy is defined as the measurement of disorderness. It is also a thermodynamic variables like pressure, volume and temperature. So that means entropy, well, it measures how random are the molecules are of a system. So if you have a thermodynamic system like this and we supply some heat to it, well, if we supply some heat to it, then the molecules start to move randomly, right? So that means the more random something is, the more entropy there is. So that means if we apply heat to a thermodynamic system, we increase the entropy of the system. So that is also the second law of thermodynamics, that the universe is always expanding. There's always an increase in entropy of the universe. Because, well, as time goes on, the universe starts becoming more and more random. Now, entropy, or let's say the change in entropy, is given as a mathematical definition as the heat supplied to the temperature, right? To the absolute temperature. So here, first case for the temperature is when, well, T is constant. So in this case, we use dq equals to mLf. If you remember in the latent heat, well, this is mass into the latent heat of fusion. So the change in entropy, well, I think this is small ds, right? This becomes mLf by T. Now, if T is, well, changes, right? It changes, then dq is equals to well, ms dt. So don't confuse S with entropy, because this S represents specific heat capacity. So that means ds becomes ms, well, right, specific heat capacity, ms dt, well, by T, let's write. So here we can get the entropy by integrating both sides. And here, well, if the temperature changes, let's say it goes from T1 to T2, that means entropy is equals to, these two are constants, so it goes outside, dt by T, so which is ln T, and goes from T2 to T1, so it becomes minus ln T2 by T1, which is just ln T2 by T1. Now, we can also derive, well, a relation from entropy and from the first law of thermodynamics. So according to the first law, the change in heat is equals to the change in internal energy plus some work done. Now let's say the temperature is constant. That means there is no change in internal energy. So dq equals to dw, and we know work done is equals to pdv. Now here, from ideal gas equation, we have pv equals to nRT. So pressure is equals to nRT by v. So that means dq equals to nRT by v dv. So nRT by v dv. Now we want the change in entropy. So here we have the temperature part. Let's just move that downward. So dq by T is equals to nR dv by v. Now here both the number of moles and, well, specific gas constant are both constant. So therefore this is equals to ds. ds equals to dq by T, directly proportional to change in volume by original volume. So that means if the change in entropy is, well, inversely proportional to the original volume, that means the more volume we have, the more, well, the more volume of the system we have, the less entropy there is, the less randomness. But the more the volume changes, the more there is entropy, which makes sense, right? Because the more something changes, the more the volume changes of a system, that means the more random it will be, right? So that means, well, the entropy is therefore proportional to volume. The change in volume, sorry. So that is it for entropy, and if you learn something new, please like and subscribe. Thank you.